In this video, we're going to get into the world according to Adam. Now, my view of the world is not that of an expert, but I do have my own conclusions that I draw based on what I think I know. Sometimes I'm right, and sometimes I have a differing opinion than conventional wisdom or even sometimes the experts. And sometimes I'm wrong. Today we're going to take on decoupling capacitors, and I have a slightly different view of where to place those on a breadboard than I have seen, and therefore I call conventional wisdom. And I'm going to explain my thinking behind that and why that differs from what I see others doing. Once again, I'm not an expert. I may be totally off base on this, and I may prove myself to be wrong at some point down the road with the decoupling capacitors. I also tried to solder up a secondary ground plane, if you will, on the breadboards, and that ends up being a fail in this video. So stay to the end, you'll enjoy that. Hi, my name is Adam. I'm building a 16-bit computer from scratch. I hope you'll join me on this journey. In part 58 of his Making a Pipeline CPU series, James came across something which I am desperately trying to avoid. I believe it's the root of a number of my problems in that 16-bit extension of Ben Eater's computer that I ran across. And I'm hoping that if I plan for it now in this build, I can get ahead of it before it gets out of control. As you can see on the picture here, there is a purple trace in the oscilloscope. And that purple trace, James, hooks it up to ground on one section of his build, and then measures ground on the other section of his build. And as we get closer in on this, you see, while the voltage should be the same and should be technically zero, there's a whole lot of nastiness going on there. He is getting all kinds of noise and ripples and incongruence between the two sections of ground in his build. And that's really what I'm trying to avoid and the purpose of our conversation today. Now, decoupling capacitors are supposed to smooth some of that out. And I know James had a number of decoupling capacitors in his build, and I know he added more to try to combat that particular phenomenon. But I believe that not only decoupling capacitors, but where the decoupling capacitors go is just as important as having the decoupling capacitors. A capacitor does not have direct connectivity. I've got my multimeter out, and you can see that it's emitting a tone and showing me that I've got connectivity when I touch the leads together. But when I touch the leads of this ceramic capacitor, there's nothing there. There's no connectivity. Same thing with this electrolytic, no connectivity. So a capacitor really has just two plates, and they sit very close together, and when you connect one side up to a positive and one side up to a negative, basically what it does is it builds up electrons and a positive charge it builds up a positive and a negative charge on the two plates that are opposing each other. One charge on one side, one charge on the other. Now, while it's handy for us to conceptually visualize that the positive charge goes to ground and that the motion of electricity is from positive to ground, the reality is that electrons move from ground up to the positive voltage potential. And that's going to be a key thing to remember as I go through my analysis of where this problem might lie and how I might go about solving this. Conventional wisdom is to have a ground plane, a very large storage layer where you have lots of electrons that can easily be liberated from the metal that's in that ground pour, ground plane, ground fill, however you want to term that. Many PCBs have several ground pours or ground fills or ground planes, if you will. I'll use ground plane from here on out. In the crude diagram I have up on the screen, let's assume that the black dot in the middle is the ground pin of an integrated circuit, and you're zoomed way in on this. And then there comes along some demand that consumes some electrons. And you end up with a hole of electrons or some missing electrons in this ground plane. Well, effectively, that becomes a relatively positive charge on that ground plane, right around that particular pin. That raises the voltage ever so slightly on the ground, which is the reference ground, which effectively drops the voltage potential at the VCC or positive pin of the integrated circuit. If you have a big enough spike of these, then you could end up changing your voltage to be zero, the voltage potential between those two pins to be zero. But electrons start to rush in and start to displace or fill these holes, and they end up crowding around the ground pin, where you end up with a more highly negative charge. And then, of course, the negative voltage, marginally negative voltage on the ground pin against the positive side ends up creating a higher voltage difference between the two of them. And eventually this settles out and you end up getting back to normal again. Now, all of this, if this is just a single spike of demand, if you will, this ends up happening very quickly and settles out and life goes on. But if you end up having repeated instances of this, you can see how a huge wave or a lot of noise can be generated on the ground plane, which can cause problems. And again, this is what I'm looking at trying to resolve today. Once again, conventional wisdom is to put a capacitor connected to VCC and then connected to the ground plane. And again, if we end up with that demand, with this bucket of electrons attached somewhere else to the ground plane, you can see how there might be waves emanating from that particular connection across the ground plane, resulting in waves, resulting in unstable ground reference against VCC. So my proposed solution, and what I think I'm going to do on this build, is to put that capacitor connected up right to the ground pin, or as close to it as I can get, and then connect the other side of that capacitor to VCC. What that does is that puts the storage of electrons right up next to where the demand is going to be. And assuming that the VCC voltage potential doesn't hang on to those electrons too strongly, then the ground pin should be able to pull what it needs from the capacitor relatively easily without creating ripples across the entire ground plane. There are in fact available decoupling sockets where you plug your integrated circuit directly into the socket. It's raised off the PCB or breadboard far enough to fit a capacitor in there between the power and ground pins. And this is effectively what I was showing in the previous slide, where the reservoir of electrons is as close as possible to where the demand is going to be. I even considered soldering capacitors directly to the integrated circuits themselves, but figured I'd end up with a situation where I could not actually seat the integrated circuit into the breadboard. So I opted not to do that. So using that as my model, what I'm going to do is I'm going to stretch the capacitors across the top of the chips such that I am connected to the VCC pin as closely as I can get it and the ground pin as closely as I can get it for each IC. Now that's going to end up blocking the labels, but I think I'm going to have to make that compromise in order to reduce the amount of noise on my breadboards. So for now, I normally hook up power right here in the corner of the board. And I have this 47, I don't know if you can see it or not, 47 microfarad capacitor. The glare is horrible. That I'm going to stuff into this power rail right here, right up next to the power supply. I'll move it over one. Right up next to the power supply for decoupling and removing some of the bounces back and forth. I've got the timer speed turned way up. Let's turn that down. Now I don't have anywhere near a large enough build. I did some brief testing today to check to see if I put ground for my probe here and measured ground so ground would go all the way across here, across to this rail, all the way back, and then all the way back over to this pin. The two sides of this switch are bound together, so all the way back over to this pin is the farthest it would travel. And there was no difference in measurement of ground there. I'm going to keep an eye on it as I go through this, but there's no difference at this point. This board is, my build is so small, so my fears are not to the point where I'm going to realize them yet. I also got some of these 0.1 microfarad axial capacitors. Got 100 of them, obviously. And I'll pull one out here. These are what I was going to try to solder across the IC from pin to pin. And if I do that, then you're not going to be able to see, for example, what the actual IC is. I'm going to be covering up the label. I also believe I'm not going to be able to get those soldered without hurting the breadboard, or without having solder travel so far down that it actually maybe even attaches itself to the breadboard. So sticking them in this configuration is not going to be ideal, or is going to be difficult to do, but would be ideal, I guess, is the way I want to term that. But if I stuff this in right here, so I'm in the pin on ground and the pin on power, and it's the next hole down, then that does almost the same thing. I've got long leads here, so I'll need to cut those down so I can actually get that to work. But at least, you can't see the IC, but I can see the IC, and if need be, I can move it out of the way. And I believe I'm going to do that for all my ICs at this point. So we'll end up with another little fast forward deal here while I work on getting that done. Again, that blocks somewhat the view of what each chip is, but the only one that's really impacted by this is the 556. And I cut the leads a little bit shorter than I'd like. I may come back and redo that so that they match up more with the right angles of these. And I don't like this one because it's bent back on itself a little bit too far. So stand by while I correct this. And I will snip just a little bit more off the length. And try to place that in again. Right here in power. And right there in ground. Okay, that's a little bit better. And so effectively what that does is that's got it wired up as close as possible. With the big difference being that the leads are a little bit longer than I'd like. There's going to be some resonance that's in there that I'll have to deal with. This capacitor here, I'm going to bend the leads a little bit better and snip it down a little bit so that I have it right up on that power rail right where it needs to be. And negative. So that's sitting right there, right next to where I plug in. And that should take care of any of the bouncing or anything like that that takes place on this one. One of the things that I understand it's good to do with the PCB is to provide some ground separation between your analog and your digital circuitry. And on the breadboard, I can probably do something similar, though not quite as effective, by these 3 rows here are not being used, but tying ground to all 3 of those rows and taking it all the way across the breadboard. So I would have to get up underneath this clock signal here and tie this row to this row, and then tie it back over here to ground, and then probably get up underneath this resistor in order to tie one of those over. And so I'm going to go ahead and do that here. Now, while I'm doing this work, I am not certain if this is going to be a benefit or a hindrance. One of the things that I know that we watch out for in PCBs as I'm reading up on how to design them is you want to avoid creating an island or a circular path for ground, because it makes things quite nasty in the PCB and can generate all kinds of problems and the like. I have effectively done that by creating a circular path around the digital logic, and I'm not certain that that's the right thing to do or the right answer. And so we'll have to keep an eye on it and see. It's something to keep a bookmark in as to where my potential problems may be coming from. Okay, so those 3 lines, these 3 here, tied these 3 here together. One is up underneath this white clock line, and then these 3 over here, which went underneath this resistor, and I shorted for a short period of time. Not sure if you caught that. But that creates kind of a ground barrier and a ground path between the analog side of this clock module and the digital side of the clock module. I could probably do something similar over here between the power supervisor and the LCD, but I'm not certain I need that. Another thing that would be nice would be if this thing actually had a ground layer, a ground plane layer. Now, mine come with this industrial sticker that once you stick it to something, it's darn near permanent. And when I got these, I also got these metal plates that I promptly collected and set aside and put in the closet and forgot about until I was preparing for this video. Now I'm holding it at an angle here because my light is right above, and yeah, there's a heck of a glare that's going to come off of that as soon as I try to do anything reasonable with it. So what I was wondering is, can this be a second layer to a breadboard? If I use that industrial sticker and now put it on the back, I effectively have, well, one side of a Faraday cage, I guess. But I have this piece of metal now sitting behind the top layer of the breadboard. And then from there, can I take a ground wire and solder it down here onto each corner of the breadboard, effectively turning this into a ground fill layer, this metal piece into a ground fill layer on the bottom of my breadboard, just like I would want to do on a PCB. I don't know if this is going to work or not. Okay, I'm going to stop me there. This ends up being a fail. The solder I have just would not bind to the metal plate. Whether that's aluminum or stainless steel, I don't know. I believe it to be stainless steel. The reality is the tin lead solder I have is for electrical connections and just simply would not bind to that metal plate the way I wanted it to. I believe I can probably overcome that by grabbing some different kind of solder, but it's going to be more closely related to brazing than it would be actually creating an electrical connection, excuse me. So while this does end up being a fail, I'm presenting it to you as fast forward so that you can watch this and maybe laugh at yourself, laugh at me while I am too. I do not end up adding the backer plate to the timer circuit at this point in time. So the next video, I really am getting into the register breadboard layout. I've got two things related to the clock module that I've parked, and I will use those to fill time if I end up having a short series, or if I run out of components or something. I've got things that I can actually work on and produce content. But in the next video, I'm going to actually get into the register breadboard layout. See you soon.